presentation, remote visit of the latest status update of the Iter construction site. And this is going to be presented from southern France by Ms. Kirsten Haupt from the Iter organization. And I think she will show you some nice pictures and maybe some a few moving pictures as well. So I'm very happy to give the virtual floor to Ms. Kirsten Haupt from the Iter organization. Please.
Thank you very much, and greetings from the south of France to all of you at your special day, your special fusion day. You see on the screen already the start, and I am going to lead you through the latest steps. I mean, we're going to go back a little bit, like maybe about 2 years, but I will show you the latest developments at the Iter project. When we talk about the development of fusion as a source of energy, you're all aware, of course, that we are doing that against the background of our energy dilemma that we are facing at the moment, in connection also with climate change and fighting the effects of climate change. We need to be aware of that when we look at that the consumption of energy is increasing. In the next 30 years. It's going to double, not just increasing, but double. So we need to find new sources of energy, in particular against the background that we want to phase out fossil fuels and decarbonize our societies. Now, with the renewables, we all like them very much, but we know that they will not be enough to meet our demands, and especially the heavy energy demands. And nuclear fission, I have just learned today that Belgium is in a similar situation as Germany, where I am from, that there are national policies that phase out nuclear fission. In Germany, we have only 3 nuclear fission plants left that I understand were supposed to be decommissioned this year. This might change now under the current political circumstances, but this is what we are looking at when we are talking about fusion. When we are looking at fusion to help with our energy transition to sustainable sources of energy, of which fusion is one. So I am going to talk to you today about these 3 main things. I will just give you a little background on Iter. Maybe for those of you who are not familiar with this, I will just go through the Iter main components so that you can judge all the photos and 360 photos that I will show you later, and also the videos that I will show. For the duration of the presentation, I allow myself to switch off the camera. I think that is maybe less distracting then. So let's go. No, why is it not going? A project here is called War. Reagan and Gorbachev talks in Geneva 5 agreed the development of fusion into their disarmament agreement, and they said there that they wanted to develop fusion as a source of energy for the benefit of all mankind. It took a while for diplomacy to arrive at the Iter in 2006, and a couple of years later, construction works actually started here. Now, Iter is an interesting project. It covers, by the member countries, it's 35 member countries. It covers about half of the world population through those countries, and 85% of the global GDP in terms of the economic might that and power that stands behind it. You see the countries on the screen. And just one extra word on the EU symbol there. So we have currently 27 member states of the EU, but the UK remains a member of Iter as well through Euratom. They struck an agreement with Euratom in December 2020. It's not been ratified yet, but the UK still contributes to the project. Another country that is subsumed under the umbrella of the EU is Switzerland as well. And you see the other countries as they are: India, Japan, Korea, Russia, the United States, and China. Now, when I'm saying here a unique formula, this is quite interesting, in particular when I introduce all the components in a moment to you. The unique formula with this organization is that it differs to the way normally international organizations are being organized, in particular financially. normally with international organizations, countries pay their to a big pot and the organization does what it does to implement its mandate. With Iter, it's a bit different. At Iter, the countries pay only 10% in contributions, in cash contributions, and 90% are paid in kind. That means that all the components are produced, manufactured by the countries themselves. So this will explain why I am mentioning certain countries while I'm going through the presentation. So that's a very unique formula, because what it does actually, it creates the expertise and the knowledge in the countries. It creates industries. It creates companies, and it also creates a sense of ownership in the countries when they participate in this project through this particular formula. Now, here you see, and this material is also available on our website. This is just an example. It shows you some of the main components of the Iter machine and who is responsible for its manufacturing and production. I'm not going to go through the details, but it just shows you as an illustration how that actually works, so that really the countries are responsible for those various components. Now, I don't know how many engineers are sitting in the room there, but everybody can imagine if you have an international project like that, where the components are manufactured all over the world, that there might be an integration challenge. We have that, of course, too. We are dealing here with 1 million components and 10 million parts, and they're coming from practically all corners of the world. So, of course, there is a big integration department with us, and in reverse engineering. It doesn't always work perfectly, but it's something that you have to count on in a project that's organized that way. Still, we have learned already from other international organizations that we are functioning as an example for this international cooperation in this particular way. Now, just one word also on the timeline. You probably all know about this, that Iter has planned to start with first plasma in 2025, and then in a multi-step approach would then lead over various steps of construction, commissioning, and operation phases to the actual start of the fusion operation in 2035. Now, you've also heard that 2025 is not going to hold anymore. We have meetings coming up of the Iter Council, that is the governing body of the organization, in which this timeline is being discussed. And we believe that by the end of the year, we will have more information coming from the Iter Council on a potential change of that first number. The second number, 2035, is, to our understanding, going to hold as the start date for fusion power operation. So I'm going to just go through the main components so that you know where the images belong to that I'm going to show afterwards. This, of course, is the Iter vacuum vessel. You can see in terms of the scale, there is a figure down below. This is the heart of the machine. This is where the fusion reaction takes place. I don't need to tell you that. You're the specialists. Just one remark maybe on the manufacturing of the parts. This vacuum vessel consists of 9 sectors, of 9 40-degree sectors, and they are being manufactured 4 by Korea and 5 by Europe. You will hear me mentioning these countries. That's basically an illustration of what I had previously mentioned as the special formula of this organization and how contributions are being handled. And that is an illustration just of the sheer size in a real picture. This is a picture of a transport of the third vacuum vessel sector as it arrived here at Iter just a couple of weeks ago. This house-like structure that you see on the trailer is actually the packaging for the vacuum vessel sector. These transports always take place at night. If you were to live here in the area, you would be already very familiar with the situation. The highways are being closed because these transports have to cross them. And I can tell you that this is also a source of entertainment for some of the population here. I have heard of families actually taking their children to see these historic moments of these transport, bringing the big components to Iter. There are other components that are very large. You see here the magnetic cage that will be the main. Its main role is going to be to confine the plasma inside the vacuum vessel. And you see the three systems in the middle. I understand you can't see my cursor, but you probably know what you're looking at anyway. This is the central solenoid, one of the strongest magnets produced. It's 13 meters high, consists of 6 modules. The lower 2 are already here, and the lowest one, this one here, is already in the assembly hall. You'll see a picture of that later. Scientists have calculated that that this magnet, when it is at full, at maximum magnetic field power of 13 Tesla, it would practically, I mean, theoretically, it would theoretically, not practically, theoretically be capable of lifting an aircraft carrier out of the water. That's, of course, a very nice image. If you want to know more about these details, we have a story on it on our website. You see the other 2 magnet systems also in dark orange here, the toroidal field coils. There are 18 of those, 2 always associated with one part of the vacuum vessel sectors. And then you see the 6 poloidal field coils, the ring-shaped round coils that are in part being manufactured here on site, in particular the 4 big ones, the 2 17-meter and the 2 24 meters. So they are really incredibly large, and they just cannot be transported by road or by ship to get here. And you see some illustrations about the implications for transport here. That's the arrival of the first module of the central solenoid. So if you go back to this picture, you see the person down below. This is what it looks like in real life. So it is indeed big, but we are getting up a size. This is a toroidal field coil on transport. So you can see here how large that is, how much space that takes up. But that's the really impressive one. That's, in terms of dimension of width, the biggest transport that we had to manage. That's the lowest poloidal field coil. That's a so-called PF6. We count from the top PF1 to PF6. This one was manufactured actually in China, but under the responsibility of Europe. So each country, for their contributions, has created a so-called domestic agency, and that domestic agency arranges for the production and manufacturing of these components. And Europe was responsible for this one, but had kind of outsourced this particular coil to China, because in the workshop here at Iter, it was not possible to manufacture 2 coils at the same time of different dimensions. So hence you see this on the road coming to Iter, a spread of 11.5 meters. And for this particular transport, we actually even had to blast some rock away from a stretch of road very close to Iter, near the village of Zhuk, because otherwise that transport would not have been able to pass. Now, this is the one of the biggest components that we have here, the cryostat. You know, the cryostat's role is to protect the environments inside, so the cool temperature of the magnets and the vacuum environments inside in the vacuum chamber, and also in the other areas within the machine. This item here is 30 meters high and 30 meters wide. The parts of it have been manufactured in India. It's been put together then in 4 sections. You see here the base section that's at the bottom, then the lower cylinder, the upper cylinder, and the lid section. The upper cylinder is currently kind of parked, stored on the worksite here. You will see an image later where you can see that. The lower 2, the lower cylinder and the base section, are already inserted in the cryostat, and I will show you pictures of that. So what you see here are the parts of the lid section. And again, you just see for the scale, just for the sheer scale, you see 2 workers here. And that just gives you an idea of how large that is. So you have 12 pieces like this, and that is the central piece that is still covered in blue foil here. It's all put together right now. I saw it actually this morning. It's now wrapped up in foil, and in October it's going to be put in storage, and then it's going to be coming out of storage rather close to first plasma, perhaps a year beforehand, before first plasma is started. Okay, now I'm going to come to the pictures. By the way, what you see here on the left side, the image, that almost looks a little bit like a flower. I always liken it to a passion flower. It looks very symmetrical as well. This is a bird's eye view into the tokamak pit. So what you see here in the center, that's an assembly tool. That's actually a little tower, about 17 meters high. And then on the other items here, I will tell you more when we get to the images. But first, I would like to say that we started the assembly 2 years ago. The actual assembly activities we started in May 2020. The official ceremony, as you can see here, we had in July. But the actual first step towards assembly was this. That's the base section of the cryostat, so the thermos that surrounds the entire machine. And you can again see quite nicely here the dimensions of it. That's 30 meters wide. You see one person, you see some persons on the picture. And it almost looks as if it doesn't fit through the gate in the back, but I can assure you it does fit, because it now sits inside the tokamak pit. Yeah, and that is really an illustration that is that can remind you of science fiction movies. I always say when I show this in presentations here on site, that's a little bit like a Steven Spielberg movie. And now let me tell you some details about this. This is as I said, the base section of the cryostat, 30 meters across, 8 meters high. And this item weighs 1,250 tons. Now, the tolerance for this operation is only 3 millimeters. So imagine the kind of precision that has been applied for the insertion of this item. Okay, this, what you see now on the screen here, is the lower cylinder of the cryostat. That's also 30 meters wide. That is actually the biggest item in dimension. That is 12 meters high and 30 meters wide. So it's really, really huge. And what you can see here already on the screen, it gives you an idea of the challenges we are facing here at Iter in moving these items. You have a nice view into the assembly hall here. On the left-hand side, I hope you can see this with a cursor. I know it's jumping, but I move it very slowly. What you see here in the V shape, that's assembly tools, and they play a very, very crucial role in the pre-assembly of the parts of the vacuum vessel. You have a second one here in the back. The wall that you see here, this white wall, separates the assembly hall from the tokamak pit. And where the orange glow is here in the back, this is where the cylinder is going. Okay, and as a little bonus at the bottom here, you can already see as the first vacuum vessel sector on the floor. So what you see here now, and now you have a perfect view into the tokamak pit from above, from the crane itself, I think. And what you see here is a thermal shield that is being inserted. This thermal shield goes into the bottom part of the base section of the cryostat. Remember, the cryostat base looked like a soup bowl. So the bowl part of the base section, that is being protected on the outside with this thermal shield. We have two types of thermal shields in the machine. You can imagine, you know all about the temperature differences. So there is a thermal shield that protects the magnets that will operate at minus 269 degrees Celsius, protects them against the heat emanating from the vacuum vessel. And in the center of the vacuum vessel, we will have a temperature of 150 million centigrade. So this temperature gradient is being dealt with by thermal shields sitting between the outside wall of the vacuum vessel and the magnets, the toroidal field coils. And what you see on the screen is on the other side, it's on the outside. So here, this thermal shield will protect the magnets from ambient temperature on the outside of the cryostat. And the reason why this component looks so shiny is because it is covered in silver. Now we're coming to the magnets. That's the small magnet that you saw before on the road. So here it is being inserted. It's the first one that's been inserted a year ago into the tokamak. It's the lowest one, obviously, so it's been the first. And here we move immediately to the second. For me, this one has a special significance because my time at Iter is accompanied by this magnet. When I arrived 4.5 years ago, they just prepared the first parts of this magnet. Each of these magnets are being manufactured by producing so-called double pancakes. These double pancakes are double layer concentric spirals of conductor cable. And we have 8 of these pairs in this particular coil here, 17 meters wide. And I saw the making of it during my entire time here. And last year, it was finally inserted into the tokamak pit. So now we are coming to the vacuum vessel itself. That's the first vacuum vessel sector that has arrived. This one coming from Korea in August 2020. On the next image, what you see here is its transfer into the assembly tools. So the assembly tools I had shown you from above, these are the assembly tools. And this is where this item has been brought in. You see quite nicely in the back, I think I can safely call them internal tourists. That's colleagues who joined to see this historic movement, actually, this historic lift into the tool. Interesting maybe for you to see, just for practical purposes, how work is organized here at Iter. You see these guys down here in the green vests. The green vest has the significance that these people are responsible for the lift operation itself. So in order to make them visible on the floor in the assembly hall, they wear green vests. They're the ones that are in charge of these lift operations. Now here we see a finally assembled module. This is what the assembly hall is for, and this is where it's got its name, assembly hall. We are assembling the vacuum vessel modules. We also call them, in Iter speak, we call them sub-assemblies. So what you see here is with the yellow arrow marked is the sector of the vacuum vessel, the first one here. In blue, the very, very thin thermal shield that I had mentioned before. You see that thin line here going around. This is the thermal shield. And on the outside here, where I have the red arrow, this is one of the 2 toroidal field coils that surround the first vacuum vessel sector. Now, and the next pictures, this is really very special. This is an operation that took place just over a week ago. We inserted the first sub-assembly, so the first vacuum vessel sector into the tokamak. So what you see here on the screen is the situation where this first sub-assembly has been lifted, or is just being lifted out of the assembly tool. So what you look at is here is the assembly, the sub-assembly. Here you see the cranes, the overhead cranes, and everything is being moved above these assembly tools. This building is 60 meters high, so there is really enough space. These tools are 20 meters high, so there is still enough room to the top. But this, of course, looks quite spectacular if you look at it from the bottom. That's the view from the bottom. So this sub-assembly has been moved to the center of the assembly hall, and now it is being moved across to the tokamak pit. And that's what you see in the next image. Look at that. So this item is coming from the assembly hall here in the back. Here you see in the front, in the center rather, this item, the first sub-assembly. And may I draw your attention to this line down below here? I hope you can see the cursor. If you can't see the cursor, there is a thin line. You see the thin line underneath the component. That is the separation from the floor on the 4th level of the tokamak building. And that is 20 centimeters, what you see there. Okay, 20 centimeters as this is being moved across. Okay, and this is now really spectacular. That's the first vacuum vessel module being inserted into the tokamak pit. What you see here is practically the end of the lift operation on the first day. The coil remained suspended for another day or 2, because for the final positioning of these large components, it takes a long time. I'm sure I'm not telling you anything new. There will be enough people among you who know this kind of procedure. The last bit from the metrology point of view just takes a very long time for to complete the final positioning. So this is really the absolute latest I can show you. And I had hoped indeed to show you also a video of this, but unfortunately that I will not be able to do. But I will pass on the details of the video to you, and maybe you can share it later. I think I have this available tomorrow, just to complete the impression of this operation. It's too bad that I couldn't include it into today's presentation. And that's the last one on that operation. That's quite interesting. You see the green vests, but this is a view from a so-called port cell. There are 44 port cells around the vacuum vessel. These are the penetrations into the vacuum vessel for everything that the machine needs. I mean, so the fuel goes through there, the cryogenic liquids go through there, electricity goes through there, whatever you need, cooling water, and a lot of diagnostics go through there. So we are using normally this opening here to take visitors inside. So if you ever make it to Iter, or you have been, perhaps some of you, you will maybe remember that you've been in this port cell to look into the tokamak pit. You will understand that this is going to be increasingly restricted as more of these sub-assemblies will be inserted into the tokamak pit, and you will also not see anything anymore. So what you see in the back here, the first sub-assembly in the tokamak pit, and in the center, this is not part of the machine. This is actually our assembly tool. Okay, further on the vacuum vessel sector, this is the third sector of the vacuum vessel sector. As I said, we have 9, 4 being manufactured by Korea. This is the third one that came from Korea and arrived at Iter on the 1st of April. It was not an April Fool's joke. It was for real. It arrived here on the 1st of April. And it came here, like I showed you before. You can see it on the right, the picture with that house-like structure. What you see on the right, this picture here, what you see here is our cleaning facility. So all the components that come to Iter, they get cleaned in this facility. Maybe you can make it out. The building inside is completely covered in plastic sheets, and the floor is covered in epoxy resin, so that really you can use all the liquids there, I mean the water, to really clean everything that goes into the assembly hall. Now, I have just talked about the center of it all, the center of the machine, but of course there is a whole plant system surrounding it. What you're seeing here is part of the heat rejection system. As you know, we are an experiment here at Iter. We are not producing electricity. We are simply producing hot water and steam. And these high temperatures, these temperatures need to be evacuated through a system, and that's what you see here, the heat rejection system that consists of various components, like the heat exchangers that you see here. We also have various basins, like this hot basin that you see here, where all the water from the plant system and from the tokamak itself arrive first, and then they're being led from here to the cooling tower, where it then is being cooled down and partly reintroduced into the system and partly taken out and controlled for its quality and put back into the environment. We are taking all of our water from the canal system here in the south of France, the Canal de Provence, and we're putting it back into the river Durance. We need to pay attention on the composition of the water because of the evaporation process. The content of minerals is constantly increasing, so there's a constant mixture of used water and new water, and the system is playing a central role in that. And before we reintroduce the water into the environment, there are also strict controls on its quality. I mean, as you know, we are using tritium as a fuel, tritium and deuterium, but tritium is radioactive, as we all know, and we need to make sure that there are no traces of tritium in the water that we reintroduce into the environment. So that is being taken care of on site as well. Another plant system is, of course, the provision of electricity to the magnets. You're looking here at one of the two buildings that do that. We have a very big switchyard here on site that is connected to the 400 kilovolt high voltage power system in France. Then there is a connection through transformers into these two buildings, and via these massive bus bars, the electricity, after being converted down and converted from AC to DC, is being brought in the building to the magnets. That is just an interesting picture, just to show you also from the logistic point of view what is all needed for the system. You're looking at a tunnel underneath Iter, where some of those 10,000 kilometers of cables are being managed on cable trays. That is quite interesting. You can basically walk under Iter, entirely under Iter, in a network of tunnels. I think there are about 3.5 to 4 kilometers of tunnels underneath Iter, and you can walk along there and you find all these networks. That's very crucial here. That's our cooling plant. That's a cryo plant at Iter. We need helium in its gaseous form at 80 Kelvin, and we need helium in liquid form at 4 Kelvin for the running of the plant. We have also a nitrogen cycle in here to pre-cool the helium. So all of that you see here. This is only one part of the building. There's another building connected in the back where we have the cold boxes. This is our compressor building. And that's this installation is the biggest cryo plant installation in the world as a single installation. And if you question that in terms of like, what about CERN? Yes, you're right. The overall installations in CERN are bigger, but as a single installation, that's the biggest one. So here, that is our control building in the making. And on the right-hand side here, this is the building of the Iter organization. In fact, I am sitting in there right now, approximately here. If you can see the cursor on the 5th floor, pretty much opposite the main building where the tokamak is. So here is our control building. And just what else you see on the image, that's the double building of tokamak building here and assembly hall here. But I get to this in a moment in more detail. And I'll stop that for now and would like to then move to the 360 images. Are you still with me? Hello?
Yes, we are.
Yeah, okay.
Yeah,
okay.
sure.
You could see everything, yes?
Yes.
Yes? Okay, so then I'm moving on. It's good to get confirmed, you know, that everything is still there. Okay, so can you see this new picture of the Iter worksite?
Yes.
Okay, I'm moving it a bit. I don't know how bad it works on your side, whether you can see it.
Yeah, it's moving and
It's
relatively
moving.
smoothly, yeah.
Okay, I'll try to be slow that nobody gets dizzy. So again, this is the center of it all. Here is the tokamak building. This is the assembly hall. If you look, I mean, this whole construction place is about 1 kilometer long and 600 meters across. The premises of Iter stretch a little bit further. It's altogether 180 hectares. But the worksite itself is limited to this area. So we've just been here in the heat rejection area that's here. You see here our cooling tower. We will see more details of this later. The grid yard is in the back here, the electrical switch yard. These two buildings here are the magnet power conversion buildings. And a little bit you can see here the cryo plant. And this is the workshop where the round colloidal field coils are being manufactured, the big ones. That's the cryostat workshop. And I had told you that one of the rings of the cryostat itself, it's outside, and this is here. But I will go to a few more images. The next one should be the switch yard. So you have a different perspective now. Just to show you where we are located. This in the back here are already the Alps. Okay, and for half a year, every year, you can see the snow up there. It looks very, very nice. And we are located right next to CEA, the French Energy Commission, the French Alternative Energy Commission. They are our neighbors. So this is where we are located. Oh, and as we can see that here, I just talked to you about the quality control of the water at Iter. This is happening here. You see 4 basins here, and that's for the quality control. This area here will house laboratories, right? And this big basin here is our storm basin. For anyone who knows Provence a little bit, when it rains here, it actually buckets down. It's a lot of rain coming down here, so we need to have provisions to collect the rainwater. That's what we are doing there. So first, I'm going to take you into, hello? I had, I think, a disruption. Are you still there?
A disruption at Iter, that's not good.
No, I don't know. Are you still with me, or am I with you?
We can
still?
hear you. Perfect. Yes, please continue.
Yeah, somebody else went out, I think. Somebody else who was in the meeting. Okay. So we are now above the two magnet power conversion buildings. I'm just moving a little bit so that you see where exactly we are. So this is how that looks like, okay? So here is the double building of Tokamak and the Tokamak pit and assembly hall, and the two magnet power conversion buildings down below. You can make out all these converter transformers here on the outside. So we have these two buildings. We are going inside now. So this is the bus bars. You can see the buildings are fairly long. And this is how it looks like on the inside. So these are the bus bars that bring the electricity then to the magnets. And what you see in the next image are the converter bridges. These converter bridges, these items here, connect the transformers on the outside with the bus bars in the middle of the building. So they're all covered in foil to protect them against dirt and pollution. So next we should go to the cryo plant. The cryo plant is located right next to the magnet power conversion building. So this is that building. As I said, that's the biggest cryo plant installation in the world. The front building here is the compressor building, and in the back is the cool boxes. So let's go inside. And this is how it looks like inside. You remember from the image that I had in the presentation. We are looking at the helium of the compressor building. So everything after that is the helium cooling cycle, and this is the nitrogen cycle. So that is used for pre-cooling the helium. And in the back of the building, you get into the building with the cool boxes. That's here. So the helium in the first room is being cooled down to 80 Kelvin. And then in this room, it is cooled down to 4 Kelvin. And then through these pipes, it is brought into the tokamak building to the magnets. So the next is the manufacturing of the colloidal field coils, which is happening on site, as I explained, due to the size of the items, 17 and 24 meters respectively, which you cannot transport. That's just impossible. Just again to show you where on site that is. And you can also see that the building is fairly large. You will see in a moment why that is. So here we are. That's the first table of the manufacturing of these coils. I'm going to turn the other way, and then you can basically look along the entire building to the end. So it's 250 meters you're looking at, with I think with about 6 or 7 work tables or workstations. The first one here is called the winding table. And what is happening here is that the original material, this conductor cable that you see here on a spool on the left, is being moved through various steps to be prepared as what we call a double pancake. That's a constituent part of the colloidal magnets. The double pancake is a double layer spiral of conductor. So you have 2 lengths of conductor coming together. You see the other spool here. What is happening here is that the conductor is being straightened, is cleaned, it's bent into the new shape. It's sandblasted to prepare it for the insulation tape that is being wound around it. It's wrapped up in this insulation tape. That's why it's white. And then it goes to the next table, and the next table is here. We call it the termination table. Nothing to do with the terminator. It's the termination of the ends. And you see 2 ends on the left here. But the termination that is happening here is on this part, actually, where the 2 inner ends of this double pancake are being soldered together. And in the later process, when these double pancakes are being stacked to become a winding pack, the future magnet, then these parts here are being connected to the double pancakes on top and below. In the next step, these double pancakes are being treated with epoxy resin so that they are being insulated This material on the outside is being insulated, is being injected with epoxy resin and then heated up to achieve rigidity and for the coil to achieve insulation. You see two identical tables. Here a double pancake is in the process of being treated. This one is being prepared. We have two of these stations because the process is very time consuming and the winding is rather fast. So we need to have two of those to actually keep up with that, with the manufacturing of the others. So what you see here is actually a final winding pack already prepared with insulation as a winding pack. So what you don't see now is inside here you have 16 levels of conductor. So 8 double pancakes inside. This looks on the top here like a railroad track, are actually parts of the mold that is being built around this winding pack for the injection with epoxy resin. The last step here in this building is then a test under cold conditions. That's what these parts are for. A tube, a circular tube, is being built for the coil. It's being inserted inside there. It's being cooled down to 80 Kelvin, put under current, and then tested for several days for its performance under cold conditions. So that's the last step. And then after that, the first one has already been inserted in the tokamak. These ones will go into storage because they are needed a lot later. Okay, we are going now into the cooling plant. So that's the cooling plant. We are in the middle of it. On the left now in front, you see the top parts. Underneath, you have two basins. You have a hot basin and a cold basin. In front, these blue tower-like structures are vertical turbines. They are necessary for the movement of the water from the hot basins, either back into the heat exchangers or to the cooling tower in the back. The heat exchangers are here on the right. We'll have another picture from right inside. So it's a maze of pipes in there. And I think it's written on all of those cooling pipes or something. So that's a very large, intricate system. And I give you another little interesting view into our cooling tower. So that's that. This is the cooling tower. It's difficult to see on the top. On the top here, we have sheets in there, corrugated sheets that create a lot of surface for the induced evaporation process. On the top, we have fans, 10 fans in funnels that create an upward draft. And so we have then a cool down process in here, and the water ends up down below in temperatures of about 27 degrees. The structure in here is a type of polymer to prevent corrosion. Right, and so here you can look out into the other parts of the heat rejection system, as we call it. And that was one of the few days here in Provence where we didn't have blue skies when this picture was taken. So we are now coming to the central part of everything, even the square. I like to call it our central square, or Times Square, actually, because here you really have a view on almost all the main buildings on the work site. So here is the cryostat plant. You see one of the cylinders outside here. These are storage facilities. In the back, we've just been there, the cooling towers. In front of us, the cleaning building and the assembly hall in the back. Here you see the cryo plant, another storage building, and the magnet building where the colloidal field coils are being manufactured. So let's go inside. We start with the cleaning facility. What you see here is a toroidal field coil. It's no longer there. It's now inside the assembly hall. I saw it there this morning, but it's been prepared here for insertion into the assembly hall and then for assembly with the next vacuum vessel sector. So just to give you a closer idea of this facility here, you see the large door where all the components come in. So that door is large enough to bring in these components that are 30 meters wide. And here you have the coil, one of 18. Now we are going into the assembly hall. So this is where everything is happening right now. I'll just move around a bit so that you can see how it looks like. We were just here. That's the door to the cleaning facility. And just a look up where the massive cranes are. And this is the assembly hall. We are taking this picture from a staircase up top. So just to explain to you some of the items here, you see here a sector of the vacuum vessel. That's sector 2 of the vacuum vessel. Here is sector 3. This is sector 2 here in one of the assembly tools. Here you see it quite nicely how it is actually located inside. And you can still see the one where I've already showed you pictures of the vacuum vessel sector inside the tokamak, because these pictures were taken at the end of April, so before this operation, before the lift operation. So you see both of the assembly tools actually have vacuum vessel sectors inside. This tool is quite interesting here. It's a very simple operation with that tool, but it's very necessary. As all these components are incredibly heavy, this vacuum vessel sector weighs 440 tons. This coil weighs 360 tons. They come in a horizontal position and then need to be upended before they can actually move on. So we have that particular tool for that. And for all those movements, we have these cranes up top. Both of these cranes are really heavy-duty cranes. When you zoom in, excuse me, you see that they have a capacity of 750 tons. So together, 1,500 tons. And when they were tested for their lift capacity, sorry, when they were tested for their lift capacity, they were tested actually to a limit of 1,700 tons to give us a really comfortable margin. So that's the view from here. We are going down on the floor now, and we are looking from the side of the vacuum vessel sector where it is being prepared for assembly. Here in the back would be the tokamak pit. Here the 2 assembly tools. We've just been here on the staircase, and that's the wall to the cleaning facility. Let's continue further on. And now we are actually right in between the 2 assembly tools. So this is the finished sub-assembly, the finished vacuum vessel sector that has already been inserted, and here is the second one being prepared. You see that no coil and no magnet, no field coil has been associated with it yet, but you can already see thermal shielding on the outside. Okay, so by these little channels where the cooling liquid is going through and the shiny surface, the silver, you can make it out. So this is the second sector being prepared. One of the coils that will be associated with it is here. It will actually then be put into this structure here. It will sit in here. We call it, it's a bit like, we call it our angels. So the toroidal field coils will be attached here, and then it will move, and the 2 coils will embrace the vacuum vessel sector on each side. What you can also see here is the crane hooks. They are massive, right? We are using 2 crane hooks from each of the overhead cranes, of the heavy-duty overhead cranes, and they work in unison. They work in synchronization. And what you can also see here on the floor is a visitor group. You can make them out by the yellow helmet. So if you were to come here to visit, and maybe some of you have already done so, you would be one of those visitors here with a yellow helmet. We have a very busy visitor program. There is always something going on. As I said, I was on site this morning with visitors, so we have a lot. You're always welcome to join this group as well, so we can organize that. Here in the back, it looks a little bit small, but it's actually, that's maybe just a perspective. This is the first module of the central solenoid that you see here, okay? It is going to be put on this support, and in fact, later on, it will be built as a tower. So this thing will go on top here, and all the other 5 will go on top here. So you will have here the tower of the central solenoid growing over the coming months and possibly years. I think we are now going into the holiest of the holy, and I would like to give you just a feel of the atmosphere when you're here on site. And you get that with this cleanliness corridor, as we call it. It's connecting the assembly hall with the tokamak. By the way, when you go through here, you will have to observe certain cleanliness protocol measures. Even when you go into the assembly hall, you see that people here, they all wear overshoes, right? They all, of course, have to wear gloves, but that's very little, the overshoes. But if you go into the tokamak pit, if you go through this corridor, you need to wear an overall, a protective overall. You need to even wear a hairnet, and you need to wear additional overshoes to keep all the dirt and dust out of the center. And here we are. We are now in the central, in our cathedral, as we like to call it. That's the Tokamak pit. Let me stop from the top. So you see the overhead. That's where everything is being inserted from the top. Coming in. What you see here on the outside, that's the bioshield. That protects the environment outside against the neutrons emanating from the chamber, from the fusion reaction, as not all the neutrons will hit the walls inside the vacuum chamber. This protective wall is 1.5 meters thick. And if you were questioning that a little bit because you see all the openings, you have a good point. There are all these openings, but on the outside of these openings, we have nuclear doors that are very heavy, very thick, 60 tons heavy, in fact, that provide that confinement function on the outside of each of these openings that we call port cells. What do you see now when you look into the pit? The central tower is just an assembly tool. It's not part of the machine itself, but under the platform on where it sits, you can see just here, you can see the first magnet inside. This is the first magnet. You can just see it here, through here. The PF6, the one manufactured in China. You remember, you have seen it on the road as well. On the outside here, this is the second magnet. That's PF5, 17-meter magnet. You remember, you've seen it also as it's been inserted on an earlier picture. So that's already in. What you also see, if you look down, is correction coils. So these pink and wrapped in pink foil here, these are correction coils. So as you know better than I do, is when you have the three magnet systems that create and manipulate and shape the magnetic field to confine the particles in the plasma, you need fine tuning, and that is being done by these correction coils. And there are several systems of correction coils. What you see here are the bottom correction coils, the X vessel correction coils. There's another complete set of internal vessel coils, but they are being introduced later, obviously. What you can also see here is these towers. These are the gravity supports for the toroidal field magnets. You can see that they are massive to manage the expansion of the coils during operation. You see here the steel plates that are arranged inside here. And let me tell you that I think, here, these two supports are for the first vacuum vessel sector that you've seen. Oh, no, it's these two. Sorry, it's these two. So that's what you've seen on an image before. The first vacuum vessel assembly has been, sector assembly has been put here. Okay, we have two more images. That's just a closer look to the downside. You can see the magnet quite nicely. The second one, you can see the correction coils quite nicely. And another image of the gravity supports, the central tower, and the outside, the cryostat. This is the cryostat in the pit. Here, the lower cylinder. Everything else here, you can't even see the base section of the cryostat anymore. Maybe one thing I should point out to you is these openings here, these oval openings. These are for one of the heating sources. As you know, there is internal heating through the current created by the central solenoid, but there are external heating sources as well, provided by microwaves, but also provided by a neutral beam. This neutral beam is coming through these openings. There is a third one behind here. The small one here is for diagnostics. So that's what these openings are for. And this is our final picture. Actually, this picture is not been taken by a drone. We were standing on the central tower to take that picture. So you're actually on the central assembly tool, and you can have a nice view down into the pit. And with this image, I conclude that presentation, and I think we can now move to the movies.
This Tuesday, the Iter project reached another milestone. A very remarkable milestone, as the 1,250-ton cryostat base was lifted into its final position inside the tokamak pit. The tension was tangible inside the assembly hall, while last inspections were performed and last instructions given. With the metrology team in position, the pilot launched a delicate procedure of balancing the hoists and synchronizing the cranes, while all eyes were on the digital gauges indicating the loads. 300 tons, and the stainless steel giant was in the air. After 24 minutes, the precious load reached its final height, took a little rest and test, to then embark on its 110-meter horizontal trajectory towards the pit. This operation surely wasn't for the faint-hearted, as the base had to be lifted above the sub-assembly tools with very tight tolerances in all three directions. But the most difficult part was yet to come, the lowering of the giant into the pit. A surgical operation requiring millimeter precision. 24 hours later, the base arrived at its final destination. Still suspended, but not for much longer.
Thank you very much.
Thank you very much for having
Kirsten,
me,
Haupt.
and I
It
wish
was
you a
really
nice end of the day of your Fusion Day.
Thank you. It was a really great tour that you gave us. Also the very new things personally for me that I have also seen. So
Good.
Thank you very much.
Thank you. Bye-bye.
I hope to see you later. Bye-bye. Bye.